Thanks very much, Tracy. Given that it's not a case study this year, and the title that I've got, it's not as easy to fit nice site photos in there and lots of pictures of rocks and geology, but I have tried where possible. So just a quick introduction about my journey to date and my career. I started at school, as I'm sure most of us have, and I have to confess I did do geology at school and ended up dropping it. But I saw the light and studied it at University of St Andrews. I then went on to do a Master's in Engineering Geology at Newcastle, and then joined Mott MacDonald in 2014. When I first joined the asset management team, and this was the kind of first opportunity for me to kind of handle large data sets and really get involved with data, and kind of emphasise to me the importance of data and how powerful it can be and help us to kind of make informed decisions. So since then, I've moved on to the engineering geology team and kind of developed the core engineering geology skills. And more recently, I have got involved with the geotechnical information management side of things. So just to start off with, I thought I'd start with an analogy from some other industries. And what the difference is between the companies either side of this line is how they've embraced technology. So for example, if we take Blockbuster, everyone still loves movies and kind of enjoys Netflix and stuff, but Blockbuster didn't really get onto the kind of the digital revolution and the new ways that people wanted to experience movies. So the key kind of take-home message from this is that we kind of need to embrace technology and really see the benefits that it can bring to our industry. So I've had an attempt at making kind of the kind of typical engineering geology project lifecycle. And the kind of when I was putting this together, the key thing that struck me was how we're not very good at getting the data kind of flowing through the project lifecycle. If we take the first stage, which is the desk study, this is the kind of like the first real time where we have the opportunity to gather as much data as possible. And loads of great information is captured, aerial photography, lots of geology. BGS have a great kind of borehole record, and that's kind of all brought into a desk study report. But all too often, that is kind of locked up in an appendix at the end of the report and sometimes struggles to make it through to the rest of the project lifecycle. So then if we move on to the ground investigation phase, we collect more data, and we have AGS, which is kind of the kind of prime example of great data management and keeping consistency from the ground investigation and passing that into the ground interpretation, and from that deriving parameters and creating the ground model. So that is kind of where we're actually quite good just now. We've got a good connection between the kind of ground investigation and ground interpretation. But then we move on to the design and the construction phases, and again, the information gets a bit lost. I've got a particular example where, for the construction, I had the opportunity to be involved in both a ground investigation and construction phases of a particular project, and there was lots of monitoring instrumentation that was put in during the ground investigation to monitor throughout the construction. But when I got to the construction phase, all the construction site people had not put the monitoring positions in the BIM model. So there was a lot of clashes with piles, etc., which meant having to do a lot of re-drilling at a crucial time when you want to know the monitoring data. So that's a classic example of where the kind of information, if it had been there, it would have been able to kind of help inform decisions quicker. So I've had a little attempt at producing a new kind of project lifecycle circle, with the key message being data being at the centre. And really the key message is kind of passing the knowledge through each stage of the cycle so that the next cycle can benefit and we can be more informed with decisions we're making. So for that graph there, what I'm kind of trying to show there is at each stage we're gathering lots of information, but when we move on to the next stage, some of that information might be lost and we might have to reprocess it. Equally, there might be information out there that we never actually obtain, or it might be that technology provides a means of kind of bringing in new information. So you can see that red line never quite meets the potential information that could be available. I've also added an additional kind of component, which is asset management, which I think is particularly important and is a growing part for our industry. More and more asset owners are kind of requiring their assets to last longer than they might have originally been designed for. And so it's important that we include that as an important part of the cycle going forward. So what I'm going to do now is just going to go through kind of each component and kind of have a few suggestions and case studies of where technology might be able to help us. On the left there, I've put some kind of key drivers that I think is important that we consider when we're thinking about how technology is going to help us, because we don't want to be using technology just for technology's sake. So for example, accuracy, is it that we're trying to kind of remove the human error element? Is it that technology will provide information that we might not otherwise have had? Can it be used as a communication tool for both kind of clients or other disciplines, or even within our engineering geology community? Does it provide efficiency, time saving, or can it provide a safety aspect? It means we don't have to put humans in positions that are potentially dangerous. So the first aspect is the desk study and site reconnaissance. And as I've said before, this is the first time we get to kind of bring data into the system. So it's kind of a key part that data is in a format that we can readily transfer it through the project lifecycle. And an important part of that is the common data environment. And that's effectively a one-stop shop for where the data is held, and that is where the kind of one source of truth is. And so that, if you've got that set up, then that kind of really helps the later parts of the cycle. And also drones is another one. I think drones is quite a hot topic just now. Lots of people like to suggest drones, and maybe sometimes there isn't as much thought about how they can benefit. So I think that comes back to the key drivers. I've just got a little case study here, a project we've been working on in the Caribbean, where they've used photogrammetry survey on a drone. So in 4 days, they surveyed 15 kilometres of road and took lots and lots of photographs, 7,600 in total. And what they did was stitch them all together to create a model that you can then kind of go back in and interpret. And I had a look at it earlier this week, and it's a really powerful tool at firstly providing a different perspective. Now what I mean by that is when you're walking along the road, you kind of only can see one perspective, but this allows you to kind of take a higher up view, and you might be able to see kind of more indicators of slope instability and things that you might otherwise not have seen from the road. Another benefit is it provides virtual site visits. As much as Tom and Matt, who went out there, probably would love to go back multiple times, for projects like these, it's not feasible. So this allows kind of like for virtual site visits, where people, if they there might be something that they want to kind of revisit, it might be something in a cutting in the roads, that they could see some potential features, they can go and review this. It also provides a good source of digital data that you could kind of create elevation models. And if it's surveyed more than once over a period of time, you can have that 4D aspect and see how things change. And obviously it was completed in 4 days, so the survey speed is invaluable there. So I've got a quick video, I'm just going to show you of it. Hopefully it's going to work. So this is just a kind of little spin round. This is effectively all the photos stitched together that you can then go around. You can notice some of the trees are a bit pixelated. Basically, it's all dependent on how many photos you take. So the more photos you take, the better the resolution is going to be. And the more angles you take it from, the better as well. So this is a really good tool if we're going back and kind of visiting, okay, we've got some undercutting there. And you could go any part of the model and really use it as a kind of informative tool. So moving on to the ground investigation stage, I can remember very well, David, you said in your talk at the 2016 Glossop lecture that standards are deteriorating, and it's hard to argue with that, to be honest. I think we have some key problems with awareness of some of the techniques and understanding of what we're trying to achieve from the ground investigation, and also a big problem with data reliability. Can we rely on the data that is coming out of the ground? So how can technology help us? Well, digital core logging is one that is kind of talked about a lot, and isn't anything new, but I don't think it's used often enough, and that could really help us with both efficiency and also the accuracy aspect. I was just speaking to someone literally yesterday who was talking about how you can kind of capture field data on your phone and build that into an ArcGIS system, which seems like a great way of capturing information and also it being georeferenced. And also some multi-sensor core logger. I believe that's being trialled at Heathrow, and also the core scanner that was used at Crossrail, which gives it a great record of the core, because we can't go back to the core once it's been dug up and it's dried up. So if we have an accurate record of that, if we have P wave velocities and kind of gamma waves, then we can have a kind of permanent record of the properties. I've also suggested there potentially smaller, high-quality GIs. Sometimes we have a bit of a scattergun approach and try and get as many boreholes as possible, which might be not the best quality, but it might be that we kind of have more targeted GIs based on where maybe the higher risk areas are. And then we have more testing. Maybe we have some geophysics, downhole geophysics, or other in situ testing that we can really kind of get to know the kind of key sites much better. So moving on to ground interpretation, design and construction phases. I know they're three quite varying ones, but I've grouped them together and put 3D ground modelling as one thing that could really help us there. I've taken a quote from the Network Rail Earthworks technical strategy I was reading, and in that Simon Abbott says, the communication of hazard, consequence and risk when associated with geotechnical infrastructure can be very challenging. I couldn't agree more, and I think as an industry we're quite bad at explaining that risk. So anything that can help us kind of communicate to the client is a great thing. So I've just got an example this is kind of more from the construction kind of side of things, and this is from Thames Tideway. What we were looking to do was help the contractor visualize where potential fractures might intersect the shaft. So we had kind of different points. You can see the red points at certain boreholes. And this is where fractures were recorded. We could then match them up and see where that was going to intersect the D-wall of the shaft. And that can kind of help inform temporary groundwater controls for the construction, and can really kind of help reduce the risk. And also it's a great tool for the client to visualize that as well. Without that picture, trying to explain that situation is very hard to a client. So from a purely communication perspective, I think ground modeling and Leapfrog is a really powerful thing. So moving on to the constructions and design verification and asset management, I've put here smart infrastructure, and this is kind of our opportunity to gain a better understanding of, once we've designed it, is it performing as we expected, and can it give us any early identifications of problems that might be developing. So this is another case study that I've been working on, where they're building a substation at the base of a landslide, and they have put in a series of piles to intersect the slip plane. And one of the key things is they've put some inclinometers, strain gauges, and surface monitoring points in some of the piles, and that is to kind of help verify the performance that they're kind of doing as they should be, and stabilising the slope. And there's also some critical infrastructure around this site, so it was important that we detected any movements early, so it didn't become more of a problem. And they've put their design verification. That's really important, because with this retaining wall that you can see here, once the ground was excavated in front of that, a few months after that photo, the design had predicted 40 mil of kind of displacement, kind of tilting, once the earth was removed. And so the inclinometers can produce kind of live data to see how that is matching with expectations. So moving on to asset management, I think I'm probably a bit biased because I've worked with the asset management kind of team, but I think this is a hugely important part. Once we've kind of gone through the rest of the cycle and constructed it, we then need to make sure that it's going to last its intended design life and last for its intended purpose. And increasingly, Network Rail is a prime example where we are asking assets to perform much longer than they were ever intended to be built for. So it's kind of a crucial part, and we need to kind of get all that information coming round the circle to help inform the asset management, and that'll help inform kind of decisions that we're able to make in terms of interventions and possible mitigation and control measures. So I've just taken another little screenshot from the Ground Engineering magazine, and in it, again, Simon Abbott says, Network Rail is aiming to become a globally recognised expert in earthworks asset management through harnessing and continuous improvement and exploiting emerging technologies. And that's really good that a client is saying that, because I think clients are the ones we're going to have to first get on board for this, and if we get their buy-in, then it should be a lot easier for us to kind of implement these small but effective changes. So they're just some of the examples of potential ones that Network Rail are looking to use in their next 3 control periods, or well, next 2, we're kind of almost into CP6. And the key thing to highlight as well is it's a range of different techniques. It's not reliant on one, and obviously ground truthing is a really important part of this as well. So I've just got one slide on artificial intelligence. You could probably have a whole other lecture on this. But what I was kind of trying to get from this was geotechnical engineering and engineering geology is notoriously unpredictable and relies on expert judgment a lot of the time. But at the same time, expert judgment is based on previous experience, and that previous experience, there's no reason why that couldn't be built into artificial intelligence to help us. I think the key thing is it's going to be a helpful tool for us, and that will be kind of supplemented with ground truthing. There's never going to replace a kind of a core stick in the ground and seeing that geology. We'll never be able to kind of replace that aspect. But I think there is different aspects that it can help with. I've highlighted kind of every stage apart from the desk study and site reconnaissance, but probably it could help with the desk study, kind of gathering all that information as well. So it could probably help at every stage that we go through. So just thought I'd finish with some challenges. We've got 4 challenges. First one being validation. We do need to make sure that the technology is robust and it can be trusted. Second one, maybe the most important one, we have to have the competency there. Everyone has to be kind of trained in it, and people need to know what the results mean, and we're not just using it for the sake of kind of using technology. I've put a little kind of thought, kind of debate in there in terms of training. Is that the responsibility of the university or us as an industry? As a kind of starter for 10, I'd probably argue it's, the university needs to concentrate on the core skills for an engineering geologist, and then it's us as an industry to kind of build on the skills from that and give them the skills that are needed for the industry. Technical standards, how are technology going to kind of get developed into the existing standards, and do new standards need to be developed because of it? And also industry culture. I think it's a very human kind of nature to stay in our comfort zone, but maybe it needs like a kind of step out there. And maybe I've put a question mark there, does it need kind of legislative change potentially? So I just thought I would finish with a quote from Professor Peter Fuchs in his first lecture. What he says is there's 10, perhaps even 20 or more years to come into clear focus. So the key kind of message is that it might take time, and there probably will be challenges along the way. So I don't think we can just click our fingers and it will happen overnight. So we need to be patient. Secondly, new ideas, test or analytical procedures, or new materials may be developed, marketed without proof of their long-lasting capabilities. So we should really kind of encourage development and not shoot them down early on and see where they might take us. Some might work, some might not, but I think that's all part of the process. And again, this is probably the most important point of all, the understanding of surface and subsurface processes of importance to engineering and for the assessment of hazard and quantification of risk. So it's that key understanding of the geology that is really key to the kind of backbone of all this technology. We could have all the technology in the world, but we wouldn't know kind of, if it's not kind of getting applied in the right way, then it's absolutely useless. So I thought I'd just end on that. We need to have that ground truthing and kind of understanding of engineering geology. So thanks very much. If you've got any questions, then feel free to ask me. I'll be at the reception afterwards. It'd be good to have a nice little debate or discussion. Thanks very much.